I want to thank organizer for inviting me to give this talk. I think my talk will be very different than Dr. Sharma's talk. I'm going to talk more fundamentals and the main aim of my talk is that, you see, we use computers, and computers use silicon chips. And silicon chips now, the speed of computers we cannot increase more further. And our prediction is that maybe the silicon technology will disappear after some time. So now the question is what you do, because information technology and most of our life really depend upon silicon chips, which are computers and cars and everywhere. Even these lighters, these lasers are produced by silicon chips. So now the question is what you do. What type of new material you can invent. Now silicon is produced by nature. Now you can't do very much. Silicon has a certain number of electrons and ions. The same thing, gold. Gold is well defined, it is found in nature. Now, if I want to convert copper into gold, we cannot do that, right? So since I came from India, in fact, our forefathers have invented a new type of material called porous. And if you touch anything, you can convert it to the gold. I don't know whether you believe it or not. That is what I was told. That I was told that you can touch anything by that material and you can convert into the gold. And that was really great when I was a child. Now that is the aim of present scientists, whether we can invent a new type of materials which we can convert anything what we like. Okay? So that is what I'm going to tell you. It is not porous, but sort of. So before I go, I'm not going to teach you very much by the way, okay? Just relax. So I'm going to tell you a little bit about. Okay, so let me tell you where from Canada I came. So I came from London. This is Ontario. London has a problem. I think my father used to complain that I'm not replying his letters. He used to write me letters, and he never got answer of his letters. And the problem was he was always writing London, UK. Therefore, all his letters, I don't know where they went, but I never got them. That is the biggest problem with our city, that there is a bigger city named London, UK, and therefore we are sort of third class or, I don't know, lower class city. So we don't get much recognition. So that is why I want to tell you that London is located between these 5 lakes. These are very famous 5 lakes. And these lakes are as big as you can put Germany, whole country you can put inside in these lakes. They are a very, very beautiful place on earth. Really, this area, Toronto, and this is the most beautiful place on earth, and especially winter. In winter, I walk to work, and there's snow. In Canada, we get a lot of snow, okay? So when you are walking on the street, and everywhere there is snow on the trees and on the lakes are frozen. When I walk, there are some lakes. It's a beautiful place. I feel that I'm walking on heaven. My wife hates living in Canada. It's a very cold country, but really I enjoy it. So I think if you have time, I think it's the best area to go. I think nearby, about 200 kilometers from us, is Niagara Falls. And I think if you want to see, I hope you have your honeymoons, right? And if you have not honeymoon in Niagara Falls, your honeymoon does not count. Therefore, I suggest both of you come to Niagara Falls and have a honeymoon, okay? Honeymoon without Niagara Falls is not counted. Therefore, it's a beautiful place. This is Canadian side. Some of you are smiling. Please come. This is Canadian side. It's most beautiful. I think if you want to see Niagara Falls, you come to Canada side. There is, of course, American side, which is very ugly looking place. Okay, so as I told you that my really aim is to really find new materials. Some of you may not heard about some of the things which I'm going to tell you, but that's okay, don't worry. So what I'm going to talk about today, I'm going to talk about metamaterials and metals and graphene. Metamaterials are new type of materials I have recently invented. And then I will talk about how you can make new type of, different type of materials like parts. So you can mix together and create new materials which have very different properties. And you can make material whatever you want to do. Like Dr. Sharma was talking about these titanium nanowires, and you can mix up and make whatever properties you like. Okay, these are some of my collaboration. As you can see, I have a graduate students and postdocs and blah, 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 and I work sort of all over the world. Okay, so let me tell you a little bit metamaterials. There are artificial materials which are not found in nature. Okay, the beauty of now research, modern research, is you have to go beyond nature. You have to create your own material, whatever you want to do. Okay, so metamaterials happen. And by the way, they were first invented by J.C. Bose, who was, of course, Indian scientist. You know, he mentioned a little bit about these materials, but people forgot after that. And suddenly, they are now very important. And, okay, Dr. Pendry from UK, he's the main guy who really wrote in 200 and that is why. And there is similar material called photonic crystals. They are also in man-made materials. Okay? And you can make them as you like. And they are basically photonic materials. Now, question is, what is photonic materials? What is electronic materials? You may have gone in shops, electronic shops, and you bought these computers and cell phones. They are electronics. Now, electronics is where electrons move and give the information. Okay? Without electrons, you cannot have computers. Okay? The electrons transport information. Now, electronic speed is quite a small speed in materials. What photons? If you use photonic of electrons, photonic speed is the speed of light. You can have very, very fast devices, right? So why not we should make a materials which are photonic materials, like gold is electronic material, okay? And silicon is electronic materials where electrons play. Now our aim is to find the photonic materials, okay? So these photonic crystal metamaterials are new type of materials which are photonic materials where photons play a very important role. And by the way, Sanjeev John, he's from London, Ontario. He did PhD from Harvard and professor in Princeton University. He came back to Canada. Ian Ivanovich is again another Canadian. They wrote a paper, and they have been nominated several times for Nobel Prize. Now I think that one of my friends is Nobel laureate from Max Planck Institute. He came last year and he spent 2-3 months with me. And he was telling that I think these three people, I think they want to include also metamaterials for Nobel Prize. Therefore, I think these three people are potential people who can get Nobel Prize. Okay, let me tell you what metamaterials are. The metamaterials are nothing but metals. You can take a metal, and you can take a metal, for example, and you take a metal sort of thin layer, about there's 100 nanometer, 100 nanometer, and make a holes inside. Periodic hole. Periodic means it's same distance, you know, and that becomes a metamaterials. Okay, it has very interesting properties, and people have made very different type. If you take a golden ring, I don't know, in marriage you get golden ring, and if you cut the golden ring a little bit here and and that becomes a metamaterial. Okay, and then you put, if you have a golden ring and you got married, cut it a little bit, and that becomes sort of a unit cell of metamaterial. So you can repeat them, and then that becomes. The size of these are about 10 nanometers, and I don't want to go in details. Basically, the basic idea of what I want to really convince you that you take a metal and make holes, you can create metamaterials. That's what. And there are many ways. There are other systems people are using to make metamaterials. Okay, there are a lot of equations. I don't want to really go because I'm a physicist and material scientist. Okay, therefore I have to use some equations. But main point which I want to tell you that when light passes, because we are trying to make devices made from photons, photonic devices. And one of the questions was asked, what is main physics or what is main science? So that's what I'm going to tell you. What is the main science behind these materials? How you can use them to make photonic transistors, photonic switches, photonic sensors, photonic computers. You can make anything out of it. So how you can work it? So basically what you do, when light falls on these materials, so here I plotted a curve here. So there is one of the properties of materials is dielectric constant. I don't know whether you have learned in your high school the speed of light depends upon dielectric constant. Okay, and air dielectric constant is 1. When light passes through a material, its dielectric constant speed decreases. So I think that much, if you know high school physics, that is sufficient to understand this. Okay. The very interesting point about this is that dielectric constant is always a positive quantity. Okay? Because the speed of light is a positive quantity. It's not negative. It's not, positive is 100 kilometers per hour. You don't have minus 100 kilometers per hour, right? So it is always a positive quantity. Okay? And all the history of science, we have always positive dielectric constant. We didn't know that there are materials which have negative dielectric constant. This is new physics totally. And J.C. Bose, for example, pointed out, there are some people who pointed out, that people laughed at that time. That what? Because being a physicist, you can really throw out of ideas. And believe me, everything what you are seeing here are due to physics. I mean it. But physics plays very, very important role in and light or tables or cars, any device you use in medical, they are all based on physics basically. So the physicists come up with very interesting idea. They found out that dielectric constant should be negative. You can see in metals are only materials which have negative dielectric constant. And that is really fantastic. You can make now new type of devices now which are based on negative dielectric constant, which were not found in nature. And therefore, what people do, they make new type of materials which are metamaterials, which has negative dielectric constant. And you can use them to treat a cancer or heart attack. Or I will give you some example of their applications. Okay, so that's what it says here. You have here. You can see this is G0. Most of them are positive here, and then certain energy, it becomes negative. Energy plays very important role. This light which is coming is certain energy. X-rays have different energy. Right? Gamma rays have different energy. So therefore, energy plays very, very important role in applications, everyday life applications. Like in medical science, you cannot just have X-rays. You cannot use normal light for X-rays, right? You have to have X-rays. So therefore, the energy is very important. For certain energy, it becomes negative. So that energy, you can change this energy. You can have control. That is beauty of this new science or nanotechnology, that you have a lot of control what you want to do. Okay? These are photonic crystals people are making now. You take these spheres. These spheres can be silicon spheres. You can take and put it in nice directions. And this can be, these chairs which are sit here, these are really photonic crystals. Okay? You put certain things in periodic structure and that become photonic crystals. And you can make them. People are making them. Okay? The question is, So therefore, if you want to have a laser light or X-rays, depend upon what light you want. These spheres are nano size. You can have 1 meter size, nano size, whatever size you want. By changing the size, you can have a different type of. I don't want to go further. Let me see. So, like here, I gave some example here that you take some sort of gold and make holes, and then you can find out very interesting properties of these materials. This is energy, by the way, and this is talking about wavelength. You can see for certain wavelength you get energy gap. Means you can see there is light flowing from here to here, and suddenly for certain energy there is a gap. I'm sure that you must have learned in first year physics. I think everyone takes first year physics, whether you are engineer or medical doctors. In Canada, everyone takes first year physics. If you have taken first year physics, I think we tell you that atoms, you have n state, quantized states, right? N1, N2, and there is energy difference, right? The energy gap, that's called. And that electron does not state. Because energy is quantized. You put one electron here and one electron here. You cannot put electron between the two. That's quantum physics. That's what Einstein, everyone. So that's what it is here. So there is a gap, and in semiconductors have also gap. Silicon has a gap, and that is why we make computers. If silicon does not have a band gap, you cannot make computers. Period. Okay? But you cannot use gold to make a computer, because gold does not have a band gap or energy gap. Right? There is a reason. So similarly, they have invented a metal photonic materials or photonic crystals which has a band gap. That's it. Our problem is solved. Now we can make a computer out of it. Right? That's what we need. We need a band gap, energy band gap. Now we can make like silicon. Then we can take silicon technology for photonic materials, and we can make anything what we like. People have not made a photonic computers, by the way. This is all on research. Okay? This is all on research. Nothing is made yet. Same thing about metamaterials. That was photon, and there is an energy gap. You can see there is an energy gap. This is photonic energy gap, not electronic. It's not electron gap. It is more photonic energy gap. Let me know when. I don't have much.
You have like 13 minutes.
Oh, okay, great. I don't need much time. You see, in the history of our science, light always travels from a straight line. This light goes from here and falls on me. You cannot bend the light. You cannot say, okay, light goes here and then goes there. You cannot, light, if I make a hole here, that light does not go to that direction. Impossible. And that is that these new materials, metamaterials, that's what they did. You can see light goes from here and you can turn it 90 degrees and it travels. This is beautiful thing. This is beautiful science. And you can really make new type of things. People are very much excited, especially in engineering and science community, that I think these are new type of materials. It is hard to make them. It is not easy to make them. And that is why it is taking some time. But I think once they are made large scale, that will be really lot of use of these materials. That's really one of the future of our society. In fact, for light always travels. Like this is like electron. It stays here. This is how we look like this is at one place. Light always travels. It does not stay at one point. This is another property of light. But you can really make a light and locate it at one point. You can make them that light stays, and these are really big achievement of science. It's not really easy to do these things. Okay, now what I was trying to tell you now. Now, question is, okay, we have this photonic crystal or photonic materials, let us say photonic nanomaterials, whatever we call it. Now, they have a photonic pad. Now, what else I can do out of it? Whether I can make a new type of other materials. So what you can do, there's a new part is called quantum dots. Quantum dots are about 100 nanometers or 5 nanometers. They are very small particles like atoms. They have quantized electronic states. The atoms have like quantized electronic states. Therefore, these quantum dots are and they are widely used in medical applications and also from other things like lasers. For example, the laser, maybe here the quantum dot is used by me. I do not know about this one. It's very common. Okay? So these are quantum dots. They are very small size. Okay, and what you can do, you can put in metamaterial together. So therefore, I have photonic material, and then I have quantum dot, electron and photon, and this becomes very interesting physics out of. I don't. Let us see whether I have time here. Okay, I think some of you may not like these equations, but let me tell you another interesting property of these materials. This is really fascinating, and that's what. Let me go maybe further. Another slide I may have here. You can see if you take metal, gold metal, about 100 nanometers, okay, like titanium. You are using titanium, which is really a sort of direct material. It is not metal, okay. But here we have to take metals. This is very important. And people are using in medical sciences also. If you take a metal about 100 or 80 nanometer, 10 nanometer, and if you throw a light on it, laser light, so what happens? Light travels along the boundaries here. If you put this quantum and this metallic nanoparticles, we call it gold nanoparticle. If you put in a blood, you inject it. That's what people are doing in mouse and other treating. You inject it, and then it is around the cancer cell. They go and collect near the cancer cell. Okay. So what happened? So you can see this is sort of cancer cell, and this is attached. This metal is attached to it. So what happened? Light is really this light is confined here. The intensity of light is given by this quantity. Just if you are taking your high school mathematics, I'm sure you will understand it. So now you can see here, this is a dielectric constant metal, and this is a dielectric constant of blood or cancer cell, and you can see E is this. So I hope you know, we don't have pen and here board, we don't have. Being a physicist, I need a blackboard. Anyway, if you have taken your high school, you know that if you divide 10 divided by, let's say, 5 divided by 1, you get equal to 5, right? 20 divided by 10, 20 divided by 10, you get 2, right? And if you divide 20 divided by 0, what do you get? 20 divided by 0, what do you get? Infinity. Huh? Infinity. Right? You get huge number. Infinity means huge number, right? Yes. More than huge. that is the beauty of this simple mathematics. That's right. And that's what Dr. Sarma was missing that. I think that was the question asked by you, that what is the physics behind it, right? I think because you're a medical doctor, you don't really care about these equations, right? So I think that is the point here. You can see, if you take, you see, here, dielectric constant of metal is negative. You can see this minus this becomes 0. 1 over 0. The electric field produced by metal is huge. It cannot happen if metal does not have negative dielectric constant. So therefore, metamaterials have negative dielectric constant. Gold metal has negative dielectric constant. And because of that, you can get this electric field. People have done the experiment and they are trying to treat cancer in mouse using this technique. Okay? Therefore, they emit huge light. You know, huge light means you go out. Yesterday, when I went outside in Germany, it was very hot like India. You know, it's so hot. Right? So that is huge light is forming us, you know. So that's why when huge light falls on the cancer, it destroys it. It melts down. So that is the basic idea about these metallic nanoparticles. Okay, so the whole thing which I was trying to tell you, that is the basic research people are doing using metallic nanoparticles. The problem with metallic nanoparticles, they are metals. They are God-given materials. They are nature. We cannot change, as I was telling you, metal, gold, or copper to go back. Okay? You cannot change it. Therefore, that is the biggest problem. That is why metamaterials have been invented, where you can change the frequency. You can go from gold to aluminum, you can go copper, you can change to any one of it. That is the beauty of these materials. They are like parts in India. Okay, there's a medical, we have quite very famous medical college, and there's one group is making these type of new materials. So what they did, they took a metal, thin layer about 100 nanometers, nanometer size, okay? And they made a hole which is 5 nanometers, you know, these holes they have made in these gold. And what they found, and they put it here, and the light is falling through, and they measure the transmission coefficient, okay? What light is falling, okay? Like this light, it consists of many colors, right? You know that. It has many colors, yellow, and red, and blue. So it has many colors. Each color has its own energy by the way. Okay? That is very, very important in application. So therefore, what they found that when light passes, they get two colors, one color here and one color here. If you take only gold, you get only one color. If you take gold or copper, you get only one color, one peak. But here you can get two peaks. If you change a little bit, you can get 3 peaks. That is beautiful. Therefore, you can really apply these type of devices. What energy you need in your treatment or in making new type of devices, you can choose what frequency you want to use. Like when you are taking camera, you know, so some cameras are working in daylight, but certain cameras work in the night. You know, the American Army has this new type of camera which no one has, and these guys can see what is going on, but enemy cannot see it. Okay, so these frequencies, energy frequencies are very, very important. Let me know. Okay, I can stop any time. See, okay.
2 more minutes.
Okay, 2 more. Okay, let me tell you very interesting. There's a new type of materials have been invented by Professor Wallace. He's a Canadian, and he worked with Einstein, Albert Einstein, and he was making atom bombs by the Second World War. Because all the scientists, famous scientists, were collected in America and Canada, and these were set. And he was a professor in MIT and he invented by the graphene. I don't know whether you heard graphene, and basically then there are 2 people really made this graphene and got Nobel Prize 2010, but he died in 2006. He would have got Nobel Prize by the way. These are not 2 people. That's what. But he, and why I'm mentioning his name, because I worked with him about 5-6 years, and we published so many papers. And coming from India, I used to call him sir. See, in India, British has taught us so nicely we call everyone sir. You know, any senior to us, which is good. You know, you have respect. You know, you show respect. And he never liked it. He said, "You call me Philip." He was a Philip R, but I never did that. Okay, so I don't have much time. Right? Okay, so I think you guys are smart people. I am sure you're understanding these slides. So I will spend 1 second every time, and I hope you will follow it, what I'm doing here. Okay. Let me show you my last slide. Sorry. Aane ke liye dhanyavad. How many of you understand, by the way? I know, Dr. Sharma, you understand, right? How many of you else understand? Okay. Okay. Now you see, another thing I tell to my students that all of you do not, I know more than you, right? That proves that since you do not know this word, therefore, it's definitely I know more than you. That's what this word. Okay, the Dhanwad means it is a Sanskrit word, and Sanskrit is, by the way, oldest language on this earth, and every language, which grammar which we use, like I, noun, pronoun, verb, came from grammar. This is the contribution of Indian language which gave us, and every language will depend upon this. So thank you very much for listening to me.